Since Pluto lost its planet status, scientists have not abandoned their attempts to detect other large objects on the edge of the solar system. After all, there is something beyond the orbit of Neptune that significantly affects the trajectory and revolution of celestial objects like asteroids and dwarf planets. And this isn't the kind of something we can detect with telescopes. Recent research suggests it could be a miniature black hole, or even a cluster of dark matter. In this video, we'll examine the mysterious ninth planet, its properties, size, and whether it is a planet at all. The question about the existence of the ninth planet became especially prevalent when scientists closely studied the movements of trans-Neptunian objects in the Kuiper Belt, an area on the edge of the solar system similar to an asteroid belt. Astrophysicists Konstantin Batygin and Michael Brown studied 6 distant objects in the Kuiper Belt, dwarf planets and planetoids, including the dwarf planet Sedna. They found that the objects followed elliptical orbits pointed in the same direction, but moving at different speeds. This was a rather unexpected discovery, and Brown even made this analogy. This kind of result is if there were a clock with 6 hands moving at different speeds, but as soon as you look up, all the hands are in the same spot. Brown implied that this type of event is very unlikely, and on top of that, the orbits of these 6 objects are tilted at the same angle, about 30 degrees downward in the same direction relative to the plane of the 8 known planets. The chance of this happening is about 0.007%. The first proposed theory was the presence of certain objects near the borders of the Kuiper Belt that would affect gravity. Therefore, if that were the case, the mass of the belt should have been 100 times greater than it is today. Computer simulations using a small planet have shown that its mass would be insufficient to align objects in this manner. However, if you run a similar simulation with a massive planet the scale of Uranus or Neptune, the mathematical model converges and practically duplicates the real-world calculation results. The work of Batygin and Brown sets limits on the possible mass of the ninth planet, the location of its orbit, and its position in the sky. According to calculations, the mass of the planet is 5 to 20 times greater than the mass of Earth, and its diameter is 2 to 4 times larger than our planet's. To see this planet directly through a telescope is almost impossible. It is too far to register in our visible spectrum, so we have to search for it using its faint infrared glow. However, with a mass of only 5 Earth masses, it wouldn't give off much heat. Additionally, such a distant planet would revolve around the Sun very slowly, so it would be impossible to detect its movement with observation alone. It's only possible by comparing images taken at different times, and this may take dozens of years. And unfortunately for astrophysicists, it's most likely that right now the planet is the furthest removed from the Sun in the northern hemisphere of the sky, with the radius of its elongated orbit on average in range from 380 to 980 astronomical units. And even all of the data collected so far does not provide a complete picture of the potential location of the mysterious planet. The search area is approximately 600 to 800 square degrees in the night sky. For reference, the full moon only occupies 0.2 square degrees in the sky. In an attempt to narrow down the planet's orbit, the researchers compared simulation results with real Kuiper Belt objects. A 4-billion-year-old model of the solar system was built. The scientists wanted to understand how the gravitational pull of the largest planets and the ninth planet could affect the orbits of thousands of objects in the Kuiper Belt. Although Batygin and Brown actually prove the existence of a certain object that influences the position of other celestial bodies, recent research conducted over the years 2020 to 2022 have cast doubt on the existence of a massive planet. In a relatively recent study from 2021, critics of the Böttigen-Brown theory have discovered about 300 new objects in the region of the Kuiper Belt, where the Böttigen and Brown theorized the presence of the ninth planet. Astronomers scanned the better part of the sky with the 20-foot Atacama Space Telescope in Chile in search of the new planet and spent 6 years studying 87% of the sky accessible from the southern hemisphere. Reportedly, a detailed examination of the orbits of objects in question revealed that every case of orbit synchronization can be explained by known physics effects except for 2 celestial bodies. But even these 2 anomalies are an exception out of 300 objects, and in a way they confirm the new theory. Why do discoveries in these orbits not coincide with Böttigen and Brown's predictions? The answer may be that the ninth planet theory is simply incorrect. However, the nature of the strange behavior of the orbits of some objects in the farthest reaches of our solar system, hypothesized by some astronomers to be shaped by an unknown ninth planet, can instead be explained by the combined gravitational force of small objects orbiting the Sun beyond Neptune. The alternative explanation, Planet 9 hypothesis put forward by researchers, proposes a disk made up of small icy bodies with a combined mass as much as 10 times that of Earth. When combined with a simplified model of the solar system, the gravitational forces of the hypothesized disk can account for the unusual orbit architecture exhibited by some objects at the outer reaches of the solar system. The researchers created a computer model of the detached TNOs as well as the planets of the solar system and their gravity and a huge disk of debris past Neptune's orbit. Astrophysicist Antranik Safilian allows if you remove Planet 9 from the model and instead allow for lots of small objects scattered across a wide area, collective attractions between those objects could just as easily account for the eccentric orbits we see in some TNOs. Earlier attempts to estimate the total mass of objects beyond Neptune have only added up to around 1/10 the mass of Earth. However, in order for the TNOs to have the observed orbits and for there to be no Planet 9, the model requires the combined mass of the Kuiper Belt to be between a few to 10 times the mass of the Earth. Another team of scientists used the Infrared Astronomical Satellite, the IRAS, and the Akari Infrared Telescope to search for the ninth planet. 2 surveys were performed and photographed over 20 years apart, giving any hypothetical planet enough time to move to a slightly different part of the sky. The scientists assumed that any distant planets would be quite close to the equatorial plane of the sky and then studied the data marking potential planets. They have found over 500 candidates. Judging by the energy distribution of their spectra, most of them have orbital distances of less than 1,000 astronomical units. This means that most of these objects were either inside or near a faint nebula. A nebula is a cloud of interstellar gas that's difficult to see with the naked eye because it emits infrared light, or simply put, heat. It turns out that all the discovered candidates are not planets at all, but rather echoes of a faint nebula. A large planet, clusters of small objects, or a glimpse of a distant galaxy. These are perhaps the simplest explanations for the unusual behavior of trans-Neptunian objects. Scientists ask themselves a logical question. What kind of object would have enough mass to change the orbits of other celestial bodies, yet not be visible to us? This prompted theorists to consider a radical hypothesis. What if the ninth planet is a small black hole that can be detected by theoretical radiation emitted around its edges, the so-called Hawking radiation? There is a contradiction that relates to the mass of such an object. Since it is believed that only the most gigantic stars are large enough to form a black hole, the black holes they would leave behind would have a minimum mass of around 5 times greater than the Sun's mass. But what if the extreme conditions of the early universe made it possible for smaller black holes to form? A group of astronomers from Harvard University plan to start their search for such objects as early as 2023 as part of the Legacy Survey of Space and Time, the LSST project. To help them find black holes in far corners of the solar system, astrophysicist Avi Loeb developed a method to search for flares that occur when a black hole collides with small objects in the Kuiper Belt and the Oort cloud, a region that could potentially contain several trillion bodies surrounding our system. The researchers say that sometimes the objects within the Oort cloud, such as comets, can interact with lurking black holes, creating a visible flash of light, possible for Rubin's observatory to detect. Thus, if scientists could confirm that a small black hole the size of a grapefruit with a mass of 5 to 10 times the mass of Earth orbits the Sun, this could provide an answer to one of the greatest mysteries of modern cosmology: the formation of black holes. However, there is another theory, most exotic and yet just as deserving as others. What if out there at the edge of the solar system there's an object made of dark matter? We see evidence of dark matter all around us. Stars that revolve too fast around the centers of their galaxies that move too fast within their clusters. A new hypothesis now suggests that most of the dark matter can concentrate into objects the size of Neptune, the so-called dark matter planets. Although these planets remain invisible to us, they can create an atmosphere out of helium and hydrogen. And this can lead to the fact that reaching critical temperatures would trigger nuclear fusion inside the planets, which would help us discover them. Dark matter forming into planets may explain why no object with a mass approximately equal to the mass of Neptune has been discovered in the aforementioned research. Scientists believe that if dark matter planets exist, they clearly formed when the universe was very young and remained static for billions of years. In the early universe, the temperature was too high, which prevented the formation of larger objects. However, dark matter does not interact with ordinary matter nor light, and could therefore freely assemble into such, quote, planets. According to this theory, instead of being evenly distributed throughout the galaxy, most of the dark matter will be inside these relatively compact spheres, with masses ranging from a mass of an asteroid to the mass of Neptune. These hypothetical dark matter planets may have first accumulated a layer of helium, since it was the first chemical element to break away from the plasma state of the early universe, and later attracted hydrogen gas, creating a dense atmosphere around the helium similar to the layers of gas around giant planets. What would we see inside a planet like that? It's hard to say. Submerging into such a planet would be very strange. A bright layer of hydrogen would be warm since it's gravitationally bound to a dense object. The friction would cause it to glow. After the layer of hydrogen, we would reach the helium underneath, and as soon as we pass through the helium, we would see nothing. Absolute emptiness. The core of the dark matter planet would be completely invisible. You'll find yourself surrounded by a membrane of luminous hydrogen-helium plasma. The flash from the ejection of matter could compete with a supernova in its brightness. In conclusion, let's address the expediency of the search for the mysterious ninth planet. Although searches have so far not revealed a single planet at the edge of the solar system, this does not mean that the search was completely in vain. The ninth planet theory has sparked an unprecedented surge in research into the Kuiper Belt and other trans-Neptunian objects. The search for Planet 9 may eventually lead to something even more significant for the scientific progress. For example, Batygin claims that the discovery of the ninth planet, which seems so strange to us, would actually make our solar system more like other planetary systems. We quote, "One of the most striking discoveries about other planetary systems was that the most common type of planet has a mass in the range between the masses of the Earth and Neptune. Until now, We thought that the solar system is missing exactly this, the most common type of planet. Maybe, after all, our system is not as unique as we thought.